Silver and diamond. While silver metal obeys Dulong Petit law at room temperature, the diamond does not. Explain why. Okay, so what is the condition for a crystal to obey Dulong Petit law at room temperature? We need to check the Debye temperature. So for a crystal to obey Dulong Petit law at room temperature, the Debye temperature should be less than or comparable to 300 Kelvin, which is roughly the room temperature. And that's because for the Dulong-Petit law is for the classical physics. And for classical physics to apply, we need to have all the normal modes being excited. So for classical physics to apply, all normal modes should have been excited. So the Debye temperature, if you remember, is given by h bar Debye frequency omega Debye divided by the Boltzmann constant Kb, and the corresponding Debye frequency, Debye angular frequency, is 6 pi square n divided by b, the number density, atomic number density, to the power 1/3 times the speed of sound, because the Debye model is for the acoustic branch, for sound waves. Okay, so let's start comparing diamond with silver. Now, if we work on diamond, the crystal structure of diamond is face-centered cubic with a 2-atom basis at 0, 0, 0 and 1/4, 1/4, 1/4. That's basically the diamond structure. The lattice constant is given here. It's 3.5668 angstroms. The speed of sound in diamond is 12,000 meters per second. It can also be found on the web, for example, in this address. So with this information, we can calculate the number of atoms per unit cell. Now we have a 2-atom basis. So from the FCC structure, we have 8 atoms at the corners, 1/8 of each inside the unit cell. So these are the contributions from the corners. And then we have 6 atoms at the face centers, half of which are inside the unit cell. So we have face centers. And then because we have a 2-atom basis, we have twice the contribution. That's from the basis. So in the diamond structure, we have 8 atoms per unit cell. Now, what is the volume of a unit cell? That's going to be lattice constant cube. So volume of a unit cell is 3.5668 times 10 to minus 10 cube, which is 4.54 times 10 to minus 29 meter cube. Now we can calculate the number density, the number of atoms per volume, and divided by V. This will be equal to 8 divided by the volume of the unit cell, 4.54 times 10 to minus 29 meter cube. So we find the atomic number density 1.76 times 10 to 29 atoms per meter cube. Now, what is the Debye angular frequency, omega d? So first we have 6 pi squared to the power 1/3 speed of sound times the number density n, capital N, divided by v to the power 1/3. So this gives us 6 pi squared to the power 1/3. Speed of sound is 12,000 meters per second in diamond. And for the number density, we obtained 1.76 10 to 29. If we take its power to the 1/3, we obtain 5.61 times 10 to 9. So the number that we have here is 2.62 times 10 to 14 radians per second. And now we can calculate the Debye temperature. Theta Debye will be h bar omega Debye divided by the Boltzmann constant. H bar is 1.055 times 10 to minus 34 joule seconds. Omega Debye is 2.62 times 10 to 14. Boltzmann constant is 1.38 times 10 to minus 23 joules per Kelvin. And this gives us, for the Debye temperature of roughly 2000 Kelvin. So that's the Debye temperature of diamond. Now let's look at the case of silver. We have crystal structure of silver is face-centered cubic. The lattice constant is 4.0853 angstroms. It can be found here. Also, the speed of sound in silver is listed here as 2,600 meters per second. So let's go through the same calculation for silver. What is the number of atoms per unit cell? For silver, we have 8 times 1/8, corners 6 times 1/2, face centers, therefore we obtain 4 atoms per unit cell. The volume of a unit cell is a cube, so we will have 4.0853 times 10 to minus 10 cube. Therefore, we obtain 6.82 times 10 to minus 29 meter cube. The number density, capital N divided by V, the number of atoms per unit cell divided by the volume of a unit cell, which is 6.82 times 10 to minus 29, we obtain 5.87 times 10 to 28 atoms per meter cube. The Debye angular frequency, omega d, is 6 pi squared to the power 1/3 times the speed of sound, 2,600 meters per second, times the number density to the power 1/3, which is 3.89 times 10 to 9, we obtain 3.94 times 10 to 13 radians per second. So the Debye temperature, h bar omega Debye divided by Boltzmann constant, is 1.055 10 to minus 34 joule seconds, 3.94 times 10 to 13 radians per second, 1.38 times 10 to minus 23 joules per Kelvin, and this gives us, for the Debye temperature, of roughly 300 Kelvin. So from this calculation we have found that the Debye temperature of diamond is 2000 Kelvin, Debye temperature of silver is 300 Kelvin. So we see that since Debye temperature of diamond is 2000 Kelvin, that is much greater than the Debye temperature of silver, which is roughly 300 Kelvin, that's at room temperature. We can conclude silver obeys Dulong petit law at room temperature, because all the normal modes are excited at room temperature, while room temperature is a low temperature for diamond. Diamond does not. Okay, so to summarize, we were asked to account for the fact that silver metal obeys Dulong petit law at room temperature while diamond does not. What is the reason behind this? So we can calculate the Debye temperature h bar omega Debye over kb, and Debye angular frequency 6 pi square capital N over V to the power 1/3 times the speed of sound. Remember that Debye model is for the acoustical branch, and we have k Debye times the speed of sound, omega Debye. So the Debye temperature should be less than or comparable to 300 Kelvin for it to obey the Dulong petit law at room temperature. That's the classical physics result. And what is the Dulong petit law? Dulong petit law basically says that the molar specific heat should be independent of temperature. It is equal to 3R. For the solids. So that's the result of classical treatment. Now we looked at diamond crystal structure, FCC, with 2 atom bases, the lattice constant and speed of sound in diamond we can find on the web, and we calculate first the number of atoms per unit cell, 8 times 1 8 corners, 6 times 1 half centers times 2, because we have 2 atoms in the bases, 8 atoms per unit cell. Volume of a unit cell is A cubed. Number density is number of atoms per unit cell divided by the volume. Then the Debye angular frequency is 6 pi squared. Number density to the power 1/3. And we multiply it by speed of sound. And h bar omega Debye over the Boltzmann constant gives us Debye temperature. So when we do this calculation for diamond, we obtain 2000 Kelvin. For silver, which has FCC structure and speed of sound 2600 meters per second, the lattice constant is a bit higher for angstroms. We obtain a Debye temperature of 300 Kelvin. So since this diamond Debye temperature is much greater than the silver Debye temperature, at room temperature not all the normal modes are excited for diamond, therefore it does not obey the Dulong petit law while silver does.